Section 5.1 is exponential growth functions. So a function is called exponential if the variable appears in the exponent with a constant in the base. So what we want to do is we want to make sure we understand the form. These functions typically take the form of a times b to the x, where b is the base of the function. So sometimes we write parentheses around it, and a and b represent constant numbers. The base is a positive number greater, or if the base is a positive number greater than 1, then we call it the growth factor. A is the y-intercept, and also called the initial value, and x is the variable and is in the exponent of b. So keep in mind that a times b to the x, right, is not the same thing as a times b to the x. So when we write a b to the x, it is actually implied that we mean this and not this. If we mean this, we would write that. So a is the coefficient out front, or the initial value, and b is the base. The growth factor is a constant greater than 1, and so b can be written as 1 plus r, where r, right, is the rate of growth. So you'll see in some of these problems, we'll give you the growth rate, and we have to know that the growth factor is the rate plus 1. So we can also write an alternative form of our expression up here by just replacing b with 1 plus r. So it will really depend on how the information in the problem is given of whether you want to start with this form or this form. A linear versus exponential growth, right? If a quantity grows by 4 units every 2 years, this is a linear relationship. So we're describing the change in y over the change in x. So y divided by 2 would be 2 units a year. However, if a quantity grows by a factor of 4 every year, then we're describing an exponential relationship, and the quantity is increasing 300% per year. So the factor b, or 4, excuse me, which is b, right, is equal to 1 plus the rate. So notice that the rate is in decimal form. So 300% is written as the number 3. A exponential function, the graph will look like the following. So we see that it's growing exponentially, so the graph turns and grows very, very steeply as we go up. So we would say that it is increasing at an increasing rate. So it's almost accelerating as it grows up. All right, so let's look at an example of an exponential growth function. So we have on January 1st of 2000, $1,000 was deposited into an investment account that earns 5% interest compounded annually. And it says answer the following. Find a model that gives the amount in the account as a function of t. Let t be the number of years since 2000. So the initial value in this problem, right, is $1,000. That's how much money we started with. We were given the growth rate of 5%, and so we convert that into decimal form. So I can say, well, f of t, oops, sorry, they told us to name our model a of t. So a of t is going to be a, which is 1,000, times 1 plus our rate raised to the t. So we can leave it in this form, but traditionally, we go ahead and added the 1 and the 0.05 together, and so we would write it as 1.05 raised to the t. Part B says, well, assuming there's no withdrawals, how much money will be in the account in 2010? So we said let t be the number of years since 2000. So that means t equals 0 is the year 2000, so t equals 10 is the year 2010. So we want to plug 10 into our equation. So usually when we're dealing with money, we round to the nearest cent, but pay attention on your exam because they'll tell you what decimal to round to, but we usually just round money to the penny unless we're told otherwise. So if I type this equation, 1,000 parentheses 1.05 raised to the 10, we see that the account has $1,628.89 because I'm rounding to the nearest penny. So, go there. So $16,028.89. C says, well, how long until the account has a balance of $15.75? So because the variable is in the exponent, this is a little challenging to do algebraically, so we can use our calculator to do this for us. So if we go to y equals, we can put the model we created in our y1. So it's 1,000, 1.05 raised to the x. And then I'm going to graph it. And I'm on Zoom Standard, so I'm not seeing the graph, which makes sense because the initial value was 1,000. So 1,000's way up here. So if I go to Zoom Fit, it now adjusts the y values so I can see the graph. So there's 1,000 where it crosses the y-axis, and we see the graph growing. So we want to know when the account has 1575. So I'm going to go back to y equals, and in y2, I'm going to plot the line 1575, and now I'm going to graph. And I want to find the intersection. So I can see it right here. So we'll go to second, calculate, intersect. It's going to grab the first curve. It's grabbing the second curve. And then when it says guess, we say enter. And the intersection is at 9.31 years. So when t is equal to 9.31 years, that's when our balance is 1575. So it says, well, what year and month did the balance hit 1575? So it helps if we split this up. So what we have, t is actually 9 full years plus 0.31 of another year. So the 9 years tell us, well, we're in 2009, right? But we get through about a third of another year. So we're somewhere in 2009. And since this started on January 1st, at exactly 9 years, we should be at January 31st. So now we need to figure out how do we convert 0.3 months to a year into months. So there are 0.31 years. And we know that in 1 year, there are 12 months. So 0.31 times 12 months gives me 3.72 months. So this is January, right? Another month, I'll write this down, right? We have January 1st. One more month is February 1st. 2 more months is March 1st. 3 more months is April 1st. And we can see we get 0.72 into April. So we get about almost 3 weeks into April, but not enough to get us to May 1st. So that means April of 2009 is when the bank balance will hit. So we can't round because we didn't quite get to the 4th month, right? So we were somewhere in between 3 and 4 months. How long does it take for the account to double in value? So if the account started with $1,000, we want to know when is A equal to $2,000. So we can do this in exactly the same way we figured out when the balance, or how long it took the balance to hit 1575. So if I go back to my calculator and I go to the graph, right, we can see this was when we set the account equal to 1575. So if I go to my y equals and I change 1575 to $2,000 and graph, there's my model. But $2,000 is off the top of the graph. So if I go to Zoom Fit, it's going to adjust the Y values. So remember, before we started this problem, we were at Zoom Standard. So this is going from -10 to 10. So now it's adjusting so I can see the line. But when we look at it, right, we can see the intersection is somewhere off the screen. So if I go to Window and I change the X value, I can start at 0 since that was when we started the account, and I'm going to take this out to 20 years and see what happens. So now when I graph it, and see how the line is at the very, very top edge of the screen? So that's okay, it would still work for us, but it's hard to kind of see it. So if I go in and zoom fit again, let's see if it adjusts this any better so we can visualize it better. So it's going to readjust my Y values with my new X values staying the same. So now hopefully I can get a little bit of a better picture of this intersection. So that's what zoom fit does for you. It adjust Y, right? So we get a nice clean picture. So now if I go to second calc intersect, enter for the first graph, enter for the second, guess, and we see about 14.21 years. I'm just rounding to 2 decimal places, but you would round to however many you were told to round to. So 14.21 years. So it said how long, so you give the value in T. If they asked for the month and year, we would then make the conversion like we did in the previous problem.